Hi everyone, we are now on the second part of our discussion on mole conversions. Okay, so if you remember in the first part of the video, we were converting mole to number of particles and mass to mole. This time we'll be having mole to molar volume, okay, and mixed mole conversions, including density related problems, right? So here are the different relationships that we can use as conversion factors, and right now we will be using the third one, which tells us that 1 mole of a gas at standard temperature and pressure is equal to 22.4 liters as long as this condition holds at STP. That means it is at at a temperature of 0 degrees Celsius or 273 kelvins and a pressure of 1 atmosphere or 760 millimeters of mercury or 101.3 kPa or kilopascals, right? So we can only use these relationships if we have the phrase at STP, at standard temperature and pressure. Okay, so right now we will be applying different concepts in our mixed mole conversions. So take a look at the first example. We are asked how many oxygen atoms there are in 3.36 liters of oxygen at STP. Okay, so now we are counting how many atoms there are for oxygen. Okay, so number of O atoms is equal to, again, we start with what we have, 3.36 liters. And take note that oxygen gas exists as O2, okay, a diatomic molecule, okay, and then that is how you know the formula O2 here. So, but we are asked to count how many atoms there are. So we provide the conversion factors, okay, that will tell us where, when, okay, or where, in which direction do we go. Okay, so the simple mnemonic that I share with my class is that you can actually interconvert number of particles, okay, just like in the diagram I've shown. So we can interconvert number of particles to number of moles, okay, and from moles we can convert it into uh, the mass in grams. Okay, so from mole to mass, right? So in converting number of particles to moles, we use Avogadro's number, which is 6.02 times 10 to the 23rd, right? We just have to remember this value. And then from moles to mass, we use the molar mass. Okay, so we can convert moles to the mass in grams by using the molar mass. But this time we do have liters, right? We have liters, which is a unit of volume. So we must know that from the previous example, the liters here can be converted into the number of moles. Okay, we know for a fact that 1 mole of oxygen, 1 mole of oxygen molecules, that's mole O2. Okay, this time we must be complete because it gets a little bit tricky now if we don't use the labels, the appropriate labels. Okay, so 1 mole of oxygen gas is equal to 22.4 liters of oxygen. And then we can cancel this one out, cancel this out, and then now we have moles of oxygen gas. Okay, but we can convert this into the number of particles. So you have 1 mole of O2. So 1 mole of O2 here, so that we can cancel. But take note that we are looking for the number of atoms. So what we can do is we can have first the number of moles of O atoms. So for every molecule of oxygen gas O2, there are 2 oxygen atoms. Therefore, it follows that for 1 mole of O2, there are 2 moles of oxygen. right? Does it make sense? It follows that in a 1 mole of oxygen gas, there are 2 moles of oxygen. So we get to cancel the moles of oxygen gas, and we now have moles of O atoms. All right, and then this value we can further cancel it out using Avogadro's number. So we know that 1 mole of oxygen atoms is equal to 6.02 times 10 to the 23rd O atoms. Alright? So O atoms there. So this is 1 mole. And then we cancel moles of oxygen. So if we carry out the operation now, that is just 3.36 divided by 22.4. Okay? 3.36 divided by 22.4 times 2, then times 6.02 exponent or to the power of 23, then we get atoms. Right? Now, we have 3 significant figures in our given, so our answer should also be reported in 3 significant figures. That's 1.81, then times 10 to the power of 23, and then the last label is O atoms. Alright, so 1.81 times 10 to the 23 O atoms. Now let's try out the next example. So this is still mass. This now entails mass in grams given the number of molecules for a gas at STP. Alright, so we now have molecules from molecules, and then we find the number of grams. So we start with grams of fluorine gas. Grams of F2 is equal to 22, or 2.0 rather, times 10 to the 23 molecules. I'll just shorten it out to molec F2. Alright, so how do we convert it to the mass in grams? So we know that this is molecules, so we are given the number of particles. So in order to reach grams or the mass in grams, we need to go through the unit of moles. Alright, so the first step is converting the number of molecules into the number of moles. So we know that 1 mole of F2 is equal to 6.02 times 10 to the 23 molecules, right? So this much molecules present in 1 mole. So we get to cancel F2, we get to cancel F2 molecules also in the denominator. Alright, now that we have the number of moles, we can proceed with converting moles to the mass in grams by using the formula mass or the molar mass. Alright, so this is now 1 mole. Okay, we need to cancel out 1 mole of F2. But sir, what is the molar mass of F2 in the first place? So we need to get F2 first, and the molar mass of one fluorine atom is 19.0. Okay, so therefore the molar mass of F2 is 2 times 19, which gives us 38.0 grams per mole. Okay, and then we have placed already 1 mole F2 here, so the numerator should be grams. So this is 38.0 grams of F2. Okay, now we can cancel moles of F2, we can cancel moles of F2, and therefore we have the following answer. So that is 2.00 to the power of 23 divided by 6.02 exponent 23 times 38.0 So we get 12.6. And then how many SFs are there? There are only 3, so we are fine with rounding it off to 6. So 12.6 and then grams of fluorine. All right, so this is now our final answer. Now let's proceed with our third example. So in here, we are asked to determine the volume in liters occupied by 14.0 grams of nitrogen at STP, at standard temperature and pressure. All right, so we start with what we do not have, what we are being asked for, so the number of liters, and then of N2. Now take note that nitrogen gas exists as a diatomic molecule, so that should be N2. All right, and then we have 14.0, which is the mass in grams of our sample. Okay, so that's what we have in our sample. So take note that in converting from volume to what liters, we need to go through the moles first. Okay, so you have here grams of N2. So what we can do is convert N2 grams and N2 into moles. All right, so the nitrogen, the molar mass of nitrogen is basically 2 times 14.01. Okay, so that gives us 28.02 grams per mole. And then again, we need to go through the mole concept first, or the mole unit, before we can start converting it into volume. So what we do have here is 14.0 grams of N2 in our sample and the molar mass of nitrogen. So we need to cancel out grams. So 28.02 grams stays at the bottom, or as our denominator. Okay, and 1 mole N2 stays as our numerator. Okay, then we get to cancel grams and 2. We get to cancel grams and 2 here. All right, and then after that, after having moles, we can convert this into the molar volume, okay, or the liters. So we know that at standard temperature and pressure, 1 mole of a gas, or 1 mole of N2 for that matter, is equal to 22.4 liters. Right? So 22.4 liters. Now we get to cancel number of moles, we get to cancel number of moles. So we now have the unit of liters, and then this is N2. So we are now at our end unit, or the unit that we desire. So we can carry on with our solution, or with our computation. That is 14.0 divided by 28.02 times 22.4. All right, so we have 11.207, and then since we have 3 significant figures, then 11.2 liters of N2 will do, right? So that's for mixed conversion problem that involving molar volume, liters, and mass. So we have to go to more than one step. All right. So stay tuned for a few more examples.